it says here, the temperature in degrees Celsius, right, in a city on a particular day is modeled by the function t, right, defined by t of t, right, and it gives you this expression, right. So where t represents time in hours, not expression, equation, where t represents time in hours from 12 p.m. or a domain interval between 3 and 9, right, based on the model, approximately how many hours did it take for the temperature to increase to 0 degrees Celsius from its initial temperature? We're screwed. No, I'm kidding. How do I do something like this? So I see the equation, right? And the first thing that I want to do is I want to graph it. But remember, all these t values, all these t variables have to be switched to input of x, right? So if I go to the graph real quick, right, and go right here, right? Whoa, why does it look so small? Right? So let me try to increase it. Boom, boom, boom. No. Boom, boom, boom. There we go. So here we go. You're gonna press control division, right? And then I have no idea what the expression, the equation was. So it's gonna be 75 x to the power of 3 minus, and I'm doing it over here on my side, and I'll just bring it back right now. 836 x squared plus 3100 x minus 4185 divided by 14 x squared plus 10x minus 35, and it should look a little something like this. Okay, careful there. Was it a minus or a plus? Let me double check. It's a minus, right? Just be very careful when you're up here, right, because your cursor's gonna be up here. So just press the downward arrow, which over here, right, you press it down, look, you go back to regular, right, operation. So there you go. I have no idea how this looks like, but there it is. Let me try to zoom out just a bit, right? So I'm gonna press my menu 4, and then I'm gonna zoom out just a tiny bit, right, just to see where I'm at. There you go, right? So there's my equation, right, I believe. So my job now, right, is to apply the domain restriction, which is, where is it? It's 3 all the way to 9. So let's do that real quick. So again, click on your graph, highlight it, and press on it again. Go all the way to the very end. All the way to the very end. Keep going, there it is, right? So we're gonna press control equals, and we're gonna press a straight line, right? And again, it's from 3, right? Control equals again. We're gonna press this one, right? We're gonna put our variable x, right? Because that's what we're using. And again, copy paste the inequality, and then we're gonna put 9. And there it is, right? So now we graphed it, we applied the domain restriction. Let's try to see what it's asking us to find. So it says here, going back to it, right? Based on the model, approximate, how many hours did it take for the temperature to increase to 0 degrees Celsius, right? So temperature is your y, right, from your initial temperature. So if I go here, right, and then I analyze the graph and try to get the minimum, what's my minimum from here? From here to here, it's this, right? 3 comma negative 3. And now if I try to go again and analyze the graph and try to get my 0, I go from here to here, right? So there it is, right? So I was at negative 3 degrees Celsius going all the way to 0. So I went from a time of 3 to 5.42. So now what do? Well, simple, just subtract both of these inputs, right? 5.42 minus 3 should be 2.42, which is really close to our answer here for D, right? And that is basically it, right? A couple of steps, right? It looks very intimidating by the polynomial, rational polynomial, right? But again, just break it by parts, right? Our input is t, right? We have to switch it to x in order to graph it. Our domain restriction, right? Because do I care about everything? No. I know the graph goes from negative infinity to positive infinity, but we're applying a domain restriction, right? And we're just solely focused on this domain restriction. So from that domain restriction, it took me 2.42 seconds, which is approximately 2.4. What do you call it? For my time, right? Not seconds, I'm sorry, hours to get to 0 degrees Celsius, right? And that's basically it. Okay, we're gonna do a little throwback, right? This was in your Unit 1 exam, right? So a lot of you guys missed this one because very simple mistakes, right? So it goes a little something like this. A ball is thrown through an open window to the ground below. So remember that, from what? From an open window to the ground below. The height of the ball in meters, right, at time t seconds after it is thrown can be modeled by the function h, given by h of t equals that whole equation, right? Which of the following describes the height of the ball above the ground? So I see this automatically. What do? Well, you go to the calculator, and I'm thinking, let's graph it, right? So if you go to the calculator and try to graph it, right? What is it? What's, again, my input? T. I don't really care about t. I need x and y in order to be able to graph this, right? So remember, switch them, right? Instead of using t, we're gonna use x. So you're gonna have negative 4.9 x squared plus 4.4 x plus 15.24, and it should look a little something like this, right? Enter, we graphed it perfect, right? So now, what do we do? Well, for this one, I don't have to apply domain restriction or anything like that, right? If I go back over here, what I want to use is my tracer, right? So it's always, my tracer is always going to start in the y-intercept. So I'm going to try to copy this somewhere over here, right? So again, are we starting from the ground? No, right? We're starting from a window, right? A building. So my first point of interest is this one, right? Right off the bat, 0, 15.24, right? I also care, right? Just play it safe. I'm gonna get the maximum, right? My maximum is 0.449, 16.23. And then logically thinking, right? If we're modeling this scenario, right? Our job is to throw the ball up, right? As high as we can, and then from up, and it's gonna go down until we hit ground level, right? If we keep going, that is not part of the modeling process, right? So we're thinking 0 as ground level. So this is what? 2.269, and all this gibberish right here, all this gibberish is basically telling you that's your 0, okay? So don't panic. So now, if I go back over here, right? Do I care anything that goes before this? No. Remember, y-intercept is the starting point. Logically thinking, right? We're trying to model this, right? We stop here, and that's it. So now, going from here, right? Our job now becomes, how much time did it take, right? So how many seconds did it take, right? So let's look at 8. The ball begins at a maximum height of 15.24. That's true, right? The height of the ball decreases until it reaches the ground level 1.82 seconds after it leaves the window. That brings up a good question. How do we know what time exactly did it take for the ball to be thrown, right? So in total, my total time was what? Was 2.2 0.269, right? Seconds, right? But if you focus here, it's telling you the height of the ball begins to decrease until it reaches the ground 1.82, right? Seconds, right? After leaving its window. If you notice, B is basically the same concept, but our times are different. So now the question becomes, which one do I consider? Well, if we go back to our model that we just created, from 0 to 2.269 seconds, it considers everything, our increasing and decreasing of the ball. But here, it's only focused on what? Because it's decreasing. So what do? Well, we're not focused solely here. We're focused on just this section. So what do? Well, 2.269 subtracted from 0.449, right? And you should end up with roughly 1.82, right? Remaining, right? It's not perfect, right? I'm just summarizing it. But that's the difference between both of these. So what else are we learning here, right? What about C? So automatically this one's out, right? After leaving the window, the height of the ball increases at a maximum height of 16.228, which is true, right? Then the height of the ball decreases until it reaches the ground 1.82 seconds after reaching its maximum height. That is beautiful, right? If you notice here, right, on A, this is true, but the ball begins at a maximum height of 15.24. That is not true. That was our window when we were over here, right? But our maximum height is what? 16.23. So, what about D? After leaving the window, the height of the ball increases at a maximum height of 16.228, right? Meters. Then the height of the ball decreases until it reaches the ground level, right? 2.269 seconds. No, we just summarize this, right? I keep saying right. Sorry about that. But for now, which one makes more sense? Well, C, right? And then there I go again, there I go. Right. So, 16.23 is the maximum, right? Not 15.24. The answer is obviously C. Boom. Okay. So, welcome to your FRQ, right, for Unit 3. Same scenario. I literally just switched the numbers, right? You can't miss. Literally, you cannot miss. Don't embarrass me, right? It says here, remember, same scenario. A local dog groomer charges services according to your dog's weight. If your dog is 15 pounds or less, the groomer charges $45. If your dog weighs more than 15 pounds but less than or equal to 25 pounds, the groomer charges $55. If your dog is over 25 pounds, meaning your dog is big, so he charges $65 plus a $2 additional cost for each additional pound over 25, right? So this is what we're gonna call a piecewise function, right? We have to create it, right? So C of X represents the cost in dollars the local dog groomer charges for the services, right? So our function notation, right? C of X. 3 different scenarios that occur here. For starters, right? $45. If your dog is 15 pounds or less. So for, how do I put that over here? Well, it's anything between 0 and 15, right? We don't include the 0. There's nothing that weighs 0 pounds, right? There's nothing. So we don't include the 0. But anything above the 0, leading up to 15 pounds, they're gonna charge us $45. That's the first equation. A piecewise, again, is made up of different equations, right? Doesn't matter if they're all linear, constants, or whatever, right? They're all put together, quadratics, cubics, doesn't matter, right? Here, they're gonna charge us $55 for a dog that weighs more than 15 pounds. So we're gonna use this 15 again, but here we're not including it. So it's gonna be just no equal sign symbol over here in the bottom of this inequality, right? All the way leading 15 pounds, more than 15 pounds, but less than or equal to 25. So again, copy, paste. But here we do include the 25 because again it says equal to 25. And then going from there, if your dog is over, what was it, 25 pounds? So for any scenario where the dog is greater than 25, we don't include the 25, so we don't put the little line on there, right? It's not equal to, it's anything greater, above 25 pounds. We're gonna be charged, you might think, yeah, they're gonna charge us $65, but not exactly. Because there is a $2 additional charge, right, for each pound over, right? So now, how do we put this into perspective? So again, yeah, you start off with 65, but now you have to include anything above, right? So we're gonna put a 2, right? And then here, since we're focused on the pounds, anything higher than 25, you're gonna turn this into a little miniature expression, right? Where we're gonna have x minus is 25, right? So every pound over, right, is charging, right? Let's say it's 26, so 26 minus 25, that's 1 pound. That's $2, right? Per pound over 25. Let's say the dog is 27 pounds, right? 27, if you input it here, minus 25, that's 2 pounds. 2 pounds, right? $2 per each pound, that's 4. And there you go, that's part A, right? So just be very, very careful, right? With that last section. So now for part B, it's saying, what would be the cost of the grooming service for a dog that weighs 70 pounds? So how do we apply the piecewise function that we just created, right? So we have to focus here on our domain restrictions. 70 pounds. It's a heavy puppy, right? So 70 is 70 between 0 and 15? No. So I'm not gonna pay 45. Is it between 15 and 25? No. So I'm not gonna pay 55. So now I have to consider this final equation, right? Because this is considering anything that's over 25. So all I'm gonna do now, x here equals to 70, right? So let's put our input, 65 plus 2, 70 minus 25, right? And then from there, just solve for it, right? 70 minus 25 is, what is it? 25 plus 25 is, that's 50.
45.
Right? Thank you, little man. 45, right? And then times 2, 65. So now you got 45 times 2, that's 90 plus 65 should be
155.
Good job. Right, that's my cameraman over in the back, right? So that's it, that's my answer. And that is literally the whole concept of a piecewise, right? You break it by parts, right? Point this way. She's dying over here, right? But yeah, that's literally the concept of the piecewise function, right? Thankfully, we don't have to graph this or anything like that, right? Because we're combining different functions, right? We're gonna play it simple. This is your FRQ. Hopefully you understand this. Hopefully you understood. You okay? You want some water? Hopefully you understood this, right? That was too much to process, I know, I get it, right? But it's okay. Hopefully you understood this. And if you have questions about this, just let me know. Ta-da! Okay, it says here, consider the cubic polynomial function f shown above. The function has exactly 2 relative extremas and 1 inflection point, right? This used to be the second FRQ, but they took it away, they turned it into a multiple choice, so can you guess? Yes. So I want you to guess? No. Should you try? Possibly, right? So now, Alright, if I look at this, over here it says that g of x equals f parentheses negative x plus 1. So we're transforming this graph, right? There's two transformations. First one, right here, inside parentheses and outside. Let's start off with the easy one. Vertical translation, right? One unit up, right? Anything inside, outside parentheses, vertical, right? So inside here we have a reflection on the y-axis, okay? Because the negative's inside the parentheses. So where's my y-axis? Right here. This one. Oh, almost, right? So now, which one do I start off with? Do I start off with whatever's inside parentheses or outside parentheses? The answer is whatever's inside parentheses. So we're gonna start off with that reflection, right? So I'm gonna take my points, and whatever's on the right comes to the left, whatever's on the left goes to your right, right? So then you have this point right here. Now it's gonna go, where is it? 1, 2, 1, 2. It's gonna go over here, ¿verdad? And then 1, 0 is gonna be negative 1, 0. So negative 2, 0 is now gonna be positive 2, 0. Something like this, right? So if my peak is over here, my peak is gonna be over here. This one, since it's right in the y-axis, we're gonna leave it alone. And it should look a little something like, not perfect, but it's something like that, alright? Something like that. Looks a little suspicious over here, but I'll do, right? And now let me switch colors, because is that my only transformation? Not exactly. Because we have to get every single point, or focus on every single point, and we're gonna translate it one unit going up. So instead of being down here, now you're gonna be up here. Instead of being here, you're gonna be up here. Here, you're gonna be up here. And then here, you're gonna be up here. So it should look a little something like that. And to think, this used to be your FRQ, right? Not too bad. Do I care about this one now? Not exactly, alright? So just be very careful. If you want, just guide yourself through one point. I did all of them, but just guide yourself through one point. Up to you. Don't overthink it, right? Just remember, consider you want to do horizontal, take care of horizontal first, and then you want to do vertical, right? And that's basically it. Hold up, time out. I forgot to mention, right? On these, they used to tell us, right, the concavities, right? I have it here and I completely forgot to go over it, right? So just remember, concave up, concave down, right? So my concavity, where from where is it concave up? Where from where is it concave down? So I like to target my inflection point, right, which is going to be right in the middle between those two concavities that splits it, right? So what's happening from here to here? Well, this is concave up, right? So what's happening to my domain? You start at 0, right? You start at 0 and you make your way this way, right? Doesn't matter if the arrow's pointing up or down, right? Domain only focuses on left or right. So I'm at 0 here at the origin, right? Or not the origin, but the y axis, and I make my way to the left. That means I'm gonna reach negative infinity. And what about over here? Well, this one's gonna be concave down, meaning that, again, I'm gonna start at 0 and make my way to, even though it's going down, this is to the right, meaning positive infinity, right? So just be aware of that for the concavities, right? And for the domain restrictions. And with that said, that's literally it. Now for sure, right? Inflection point, just eyeball it wherever it's at, right in the middle, wherever you think it's gonna cut the concavities, and there you go. Typo. This goes from negative infinity, sorry, to 0. But yeah, that's it. Nothing fancy, right? Nothing fancy besides my clothes, and that's it. Alright, let's call it.